Okay. Welcome back. Lovely to have you back. Lovely to be back. I am really glad to be back. So, yay, we are now at the turning point of the semester where things turn around and we start having half the pace that we've been going as far as chapters being covered. So we're covering a chapter per week instead of per day. That's the good news, right? Yay! So today we're going to go over one-way ANOVAs, one-way independent groups of ANOVA, the PowerPoint and the worksheet, homework worksheet, and the RMD file are all up. I will tell you that just came in. If you click on the RMD and download it, it will not have the RMD header, which is frustrating me to pieces because if I go into the GitHub where it lives, where it's getting it from, it has the header. So you can either add the YAML header, copy and paste it from any other homework you've ever done, or your other option is to download the homework RMD from files. If you go in Canvas, if you go to files, all the assignment RMDs are in here, and these are the right ones. So you can download them from within Canvas if you want, and it will for sure have the YAML header. I cannot figure out why that download link will not include the YAML header. I gave up after a half hour because class had to start. So we're going to do this PowerPoint, and we're going to start on the one-way ANOVAs. Today will be more of a lecture-ish conversation day. And then when do we come back? Wednesday will be more of a how-to using R to do one-way ANOVAs day, okay? So it's more of a lecture, more of a lab type split from here on out. So before we do go into Chapter 12, I wanted to kind of go over the exam. Yay, exam, right? And I will be looking through all the homeworks and making sure points are given to you appropriately. I did not get that done over the weekend because the swim meet took over our life, but now that's over. Hurrah. So let's look at these test questions and see how you think you did. So did it show you any of the marked correct or incorrect?
Yeah. It shows all the multiple choice.
Did it show you the right answers or just whether or not you got them right?
Just got them right.
Got them right? Oh, okay, so if the results of a statistical test indicate that we should retain the null hypothesis, the most reasonable way to state the conclusion is 2, the second one? I think I have to, let's see. There we go. The correct answer is the second one, yay! There's not sufficient reason to reject the null. Number 2, if we draw 2 samples from the same population, one with 100 cases and one with 25 cases, for which sample will the estimated standard error be smaller? What's the formula for standard error? Standard deviation, or sigma over square root of n. So when is this going to be smaller? When we're dividing by a bigger sample size. So the answer is sample with 100. Oh, look, it's showing us correct answers. Okay, a researcher wishes to test the theory men and women differ on a measure of personality. The researcher draws a sample of 35 men and 35 women. Convenient that they're the same sample size. The sample means on the personality measure are 46.7 and 51.4. Why can't the researcher conclude just by looking at them that the difference of 4.7 means that the population difference is not 0? What are we missing? What piece of information are we missing here? Do we know the standard error? Well, we know the sample sizes, but do we know the standard deviations? No. What if the standard deviations are 40 and 50 respectively? Then a difference of 4 and 5 is not much at all. Okay, researcher finds correlation between obesity and satisfaction with life in general is negative 0.74, and that this correlation is statistically significant. Why can we not conclude either of those things?
Well, we don't know anything about the study, how they did it, so we don't know if it was
Causation. Why can't we? Both of those first 2 statements imply causation. What's in the first option? what's the word that implies causation? Makes. And in the second one, it actually says causes. So both of those statements imply causation. And is there anything here about that this was randomized or just observed? No. If this was an observational study, what's the quote? Observational studies, association does not imply causation. Oh, did you like all the output? You're given code and output, both, right? Was that nice? Was that expected? Yeah. Okay. So what's the difference between these two set t-tests? Let me turn down the lights a little bit. The sample sizes are different? No. Degrees of freedom are different. In this first way, it's a 2-sample t-test. Degrees of freedom are 16. In this second way, we've changed to var.equal equals false. So instead, it's doing the Welch's 2-sample t-test. So our degrees of freedom is a decimal quantity because it's taking into account that we have 2 different sample sizes and or 2 different standard deviations. The spreads, the variances are not equal. Versus here, this one is treating them as if they are homogeneous in variance, that the variance or the standard deviation between the 2 groups is the same. Which one should we be using in this case? The bottom one? Let's see. Levine's test was run to assess one of the assumptions. The results of Levine's test, what does this Levine's test p-value equals 0.034 tell us? There's a significant difference between the variance or standard deviation, the spreadness in those 2 groups. So we should be using this second set of results, the second analysis. We should be doing Welch's separate variance, not the top one is doing the pooled variance. So we should use the bottom one, not assuming equal variance, because Levine's test showed that we had violations of homogeny of variance. Or we don't have the same variance. So interpret the results of the t-test you choose. In this interpretation, state your conclusion regarding weight and sex using APA style. Make sure it includes the test statistic, the significance, and the confidence interval. Anyone want to give it a shot? Male, female. Go for it. What's not significant?
The difference in the means between the male.
Yeah. In our samples, males had a higher weight. This is weight, right, in kilograms? But the difference between the 2 is not significant. So there is no evidence that men really do weigh more than women in this population, wherever these people are coming from. Okay. That one. Okay. And then we had, what's this one? Oh, well, you're supposed to say, the first thing you're supposed to say, what 3 analyses were performed? What's the first analysis? What would you call that? Descriptive statistics. What's the second one? Correlation analysis. And the third one is regression, or linear regression, or simple linear regression if we're going to get really fancy, right? Okay. So those are our 3 things that we have. What assumptions are required for the last analysis to be valid? For the regression to be valid, what are our 3 assumptions? And how do we test each? Normality. Bivariate normality. Oh, the very, very first one is that we have independent random samples. How do we test that? You can't. You just have to plan as well as you can. The second one is normality, hopefully bivariate normality. How do we look at normality? How do we assess that? Plot, what kind of plots? QQ plots, box plots, or histogram. Yep. We can use Shapiro-Wilks if it's a smaller sample size, and that other one that I always forget the name of if it's a bigger sample size, which we rarely have. And then the third assumption, homogeny of variance. And how do we assess that? Levine's F-test. Yep. Okay. And what's the conclusion in APA? Most important numbers from the 3 parts. Okay. What does the regression tell us? We've got verbal and quantitative SAT scores.
They're significantly positively correlated.
Here's our multiple R squared. Here's our slope. Our slope is significant. For each point higher someone has a verbal score, their quantitative is 0.66 higher. If we look at the correlation is 0.64. It's moderately strong. There's pretty good correlation between the two. Got the averages up there. There's a lot of different ways you could write that up. I get to read them all. Yay. Okay, last part. I used to teach high school math, so this is interesting to me. So they have the traditional way and the new way of teaching geometry. Why would they have done a paired test in this? Did they do it paired? Yeah. Why would they do a paired test in this case?
They want to figure out before using new teaching method and after using.
Well, why not just divide up my 16 students into 8 and 8? Why take the time to match them and then randomize each pair? Match them into 8 partners and then randomize in each pair. Why not just randomly split them in half?
The correlation makes it easier to get significant results.
Easier to get significant results?
If there is a correlation.
Not necessarily easier.
Doesn't it have to do with the power? That there's increased power?
There's increased power when you match if the thing that you match on plays a role. So what are they matching on here? Prior math scores. If they had just flipped, randomly divided 16 students, could they accidentally have had the worst students in all the worst students in one group and all the best students in another group? It might happen. Randomization should make sure that our groups are about equal as long as our group sizes are big enough. How big are our groups? Are they very big? 8 and 8's not very good. Not very big to have randomization ensure that the 2 groups would have equal makeup with regard to prior math ability. So they would match them to ensure that the 2 groups are going to have about the same spread or breakdown of prior math ability, or at least math scores, in these 2 groups. Why don't they give each kid new and traditional both?
Because you teach them the same concept, but just different.
Yeah, what? Carryover effect, because if you teach them the unit with the traditional way, what's going to happen when you teach the new way? They already know it from the first one. That effect would carry over and contaminate the second time. So that's why you only can give them each kid one of the 2. You can't give them both. Okay? So what were you asked to say? Well, yeah, why would you bother? What's the benefit? The benefit is we're able to control for the possible confounding effect of prior math ability. Control for the possible confounding effect of prior math ability so that we don't end up inadvertently having all the best students in one group and all the worst students in another group. And then the last thing, oh, no. Oh, do you think it's adequate to just go on their last Math score? No? What else would you like to match on?
Give them pre-test for geometry.
Maybe a pretest specifically in geometry, because what was their prior math class was probably algebra, and it might have been a year ago. I don't know.
Well, it could be dependent on how good their previous math teachers were.
Yeah.
Or their learning styles, like if that was something that aligned.
Yeah, so maybe they got a bad score because of something else.
Yeah.
Yeah.
Depending on what group they were assigned into.
Yeah, maybe they got Miss almost retired and she's already checked out. Yeah. Okay, and the last one, not in APA. You were supposed to tell me what the results meant. What did these results show? What's not significant?
There's no significant
Difference would be traditional and
There's no difference? But look at that. The new way, they got a lot higher of an average. That's a higher average. We should teach the new way. There's other confounding factors maybe. We tried matching and we did randomize within pairs, so we've taken care of a lot of possible confounding. We can't rule out everything because there's still, this is not indisputable proof, right? See, this is why taking statistics is important, because a lot of people will look at that and say, that's a higher average. We should do that new thing. But what they're not taking into account is the standard deviation, the spread, and the sample size. This is only 8 and 8. Even if those were big, they're different by an average of this. They got higher by 3 or 4 points, but the spread is 8 points. So if you were to redo this with another set of students, you might see the reverse trend. So this is very, very important. In statistics, we're just not looking at the average, but we have to also take into consideration the spread. That's why today when we start looking at analysis of variance, ANOVA is analysis of variance, but we're comparing averages. Because every time we compare averages, we have to compare it using the measuring stick of how big is the spread within the groups. If the groups have a lot of spread inside of them, then that's, the spread inside of each group is 8. And if the groups themselves only differ by 3, that's not very much because it's with regard to the spread within a group. That's why we call it analysis of variance, even though we're comparing the averages. That always confused me before, why they called it analysis of variance.
So can sample size be considered?
And sample size, yeah, because we're comparing them with regard to the standard error, which is spread and sample size. So spread, the standard deviation or the variance, and sample size both are important in deciding if two average numbers are significantly different or no evidence that they're different. And that's statistical thinking. Yeah. Yeah. Is that this one? I don't have, they're not numbered on mine. Which one does?
Can we use Levin's test for both pooled variance test and the separated variance?
We use Levin's test to decide if we should do a pooled variance or a separate variance. It's like it's the deciding factor. So we have our two groups, and we do Levin's test to see if the spreads, if the variances or the standard deviations, if they're similar, then we do the pooled variance test. If they're not, then we do the separate variance test. I gave you both and told you what Levin's test said, and you had to decide which set of results to look at. Yeah. How about I promise you to have the grades up tonight on the test? That might be good? Okay. I got to tell you that so that I'll do it. Okay. All right. So One-way independent groups ANOVA. Anyone have any other questions besides scoring and grades? We ready to shift gear into ANOVA?
When writing up the APA style,
APA style.
how to write out the linear regression result?
Regression results. That's a good question. Okay, so which one, where's our regression? Is it down here? Yeah, here's the regression, right? Okay. I actually, oh, where is it? Where is it? Oh, it's not here. It must be in my bag somewhere. I got my pen fixed. I had to have, remember how my pen wouldn't write on my screen? I had to have IT reinstall something on my computer. Like it's a problem with Windows 10 update. Okay. All right. Woohoo. Okay, so here are the results. So this is our beta, or our slope, and then this is the p-value that goes with it. So usually when you would write this up, you would say, first you'd talk about the averages of the verbal and the quantitative, and the correlate were positively correlated. And then here we can say in regression, you can say it a lot of different ways, but regression analysis found that that for each point higher on verbal, on verbal, the quant score or a 2/3 point increase in quant score. Regression analysis found that for each point higher on the verbal, a 2/3 point increase in quant score was associated. That's really poor English, right? But something to that effect. And then you would say B equals 0.66, because that's our slope, and its p-value. Usually we don't write the t-value with it, and we just say p less than 0.001. B is used for the slope, for the beta, for the coefficient, the estimate in regression, just a B. In other, I think APA 6, they let you, there was always confusion. For the slope, should you use a beta, the Greek beta, should you use a capital B, or should you use a lowercase b? People ask me all that time, which of these should I use for the number that's the slope? And in APA 7, it says you only use the beta when you're talking about the population. You use a capital B when you're doing SEM, and you use a lowercase b if it's a regression slope. That's the new APA 7 rule. Now, am I going to take a point off if you didn't do that? Not necessarily, no. But that's the new APA 7. Most things are still, if you do APA 6, they'll accept it. Journals are slow to adapt. But for regression, we should use the lowercase b for a regression slope.
So with that 2/3 point increase, wouldn't that be a decrease? Because aren't you doing 0.66 times SATB, which is predicting SATB?
We don't multiply it by 0.66. We add 0.66. So if you have two kids, say you had two students, and one person, their verbal was a whole point higher, then their quant would be 2/3 of a point higher. So if they were if we think about the slope, yeah, so we have verbal and quant. So if they're different by 1 point on the verbal, then they're different by 0.66 on the quant, because that's the regression line slope.
I see what you mean. Okay.
So the rise is 0.66 over the run is 1, because the slope is 0.66, and that would be over 1.
Okay, I get it. The wording
Yeah.
was just.
Yeah, the wording is awkward, and that's why I don't have this auto-graded, because I want to read what you wrote and write something back to you.
Okay.
Okay? So this is how much the y variable, the rise, for a run of 1. So if someone has a essay verbal that's 10 points higher, then their quant's going to be, it's going to go up 10 times this. So that would be 6.6 points, 6.6 points higher.
Okay.
Yeah. Good question. Yeah. So that's kind of that languaging that I just wrote there is like one way. Usually we just say verbal and quantitative were positively correlated, and you have the correlation, and then put the B of this. And we usually don't have to say 1 point with 2/3 of a point, because we assume that all the time when we write, what you write, how you write it, what details you include depend on who you're writing to. So it's what your audience is. And most of the time when we're writing for a journal article, it's assumed that people have taken this class or something very, very similar. And if you say B equals 0.66, that they know that means the slope is rise of 0.66 for a run of 1. Now, you're just currently learning it, so I tried to write it out like verbosely, but usually you just say, yes, there was a correlation, and you can give R equals whatever it was, and then what the B is. And they'll both be significant. The correlation and the slope will always have the same p-value if your regression only has the one predictor in it. Right? This says 2 times e to the negative 16. And if we look here, it's, oh, yeah, it just gives it to less than 0.001. Yeah. If you have other questions about the test and your specific test in particular, just stay after class or send me an email. Like I say, I will grade these tonight, so they'll be done. Okay. So, Chapter 12, ANOVA. I'm going to just download the PowerPoint right from the website so that it's exactly the same thing if you want to follow along and take notes. Okay. So let me preface this with saying, almost none of you will ever use an ANOVA as your final analysis ever in a real life example. And for that reason, I find this class a waste, a little bit, that we focus the second half of this class all on ANOVA. But the reason that I still teach this class and enjoy teaching this class and believe in this class is because the things that we're going to focus on while we're learning ANOVA methods totally transfer over to regression and other techniques. And that's why this class is called Statistical Foundations, because we are going to get the foundational ideas while using ANOVA, and those ideas carry over. Now, you will use ANOVA as part of an analysis. It just won't be the final analysis. It will be like an intermediate step. And I say that, I mean, please, if you find an exception, come and find me wherever you are. Send me an email and show me that I'm wrong. I'm saying that based on the last 15 years of me working as a statistician in your fields. There are fields that use ANOVA as their final analysis, but they're almost always agriculture, because that's where ANOVA was developed. Because a lot of the assumptions are very hard to meet when you're doing observational data and human subject design, and you don't have full control on people's lives. It's just a fact. But we're going to learn how to not lie with statistics, but to tell the truth. So here's an example. Try to pick out what is different about this versus what we've done up till now. Dr. Vitro randomly assigns 30 individuals to one of 3 study groups to evaluate whether one of 2 new approaches to therapy for adjustment disorders with mixed anxiety and depression moods are more effective than the standard approach. Any red flags? What's new? 3 groups. Yep. Up to this point, we've done t-tests. T-tests can handle 2 groups. Our correlation could handle it if we had continuous or 2-level variables. Correlation cannot deal with, well, Pearson's correlation coefficient cannot use 3-level variables, only continuous or 2-level. And t-tests, you can only have 2 groups. So ANOVA is extending a t-test. Instead of just 2 groups, now we can have more than 2 groups. That's the new thing here. So participants are matched on current levels of anxiety and depression mood at baseline. Scores on the Beck Anxiety Index and the Beck Depression Index are collected after 2 months of therapy. So we're still going to have continuous measures we're comparing, and we're still going to compare the averages. We're comparing the means, just like we did t-tests. The whole key here is we have more than 2 groups. Dr. Kreff wishes to assess differences in oral word fluency among 3 groups of participants. Again, there's the key, 3. These are right hemisphere strokes, left hemisphere stroke, and healthy controls. Their scores on the COWAT are collected from 20 participants per group, and the means of the groups are compared. So we're going to compare means between usually more than 2 groups. So some vocab. Sometimes when we talk about these, we say we call it an experiment if the participants are randomly put into their groups. Like if we randomly manipulate, it's the researcher who decides who gets treatment, who gets placebo, who gets what. That's an experiment. We call it experimental design if we have assigned the groups. If we randomly select from pre-existing groups. So I might randomly sample men and then randomly sample women. Randomly sampling separately, we can treat them as if it's an experiment, usually. What we can't do is if we get one group and then we divide them based on who's men and women, even though we took one sample. That's not an experiment, that's observational. We can still do an ANOVA, but we need to know that the vocab's a little different. You also might hear the terms fixed and random thrown around. Fixed effects are levels of a factor that are chosen by a researcher, or all possible levels of a factor. So if we were doing gender and we are going to say we only have male and female, that would be a fixed effect. If we had first child, second child, third child, and we're going to say that's all we're looking at, that would be a fixed factor, would be birth order, first, second, or third. Random factors are things where there is a random or hopefully at least representative subset. So our subjects are a random subset, or at least representative subset of all possible subjects. Sometimes we can look at like nurses that are working within hospitals, so we might randomly select hospitals, and then within each hospital randomly select nurses. That would be, nurses and hospitals would both be random effects. I wouldn't get too worried, but fixed and random are terms that are sometimes used with this kind of analysis. More commonly, I see the terms independent versus repeated factors, or between subjects and within subjects. This is terminology we're going to use for the rest of the semester. So between subjects are things that are different between the subjects. So these are grouping or independent variables. So gender, if we're talking people, we could use gender, we could use birth order, we could use depressed versus not depressed, typical developing versus language impaired. It's a grouping variable that people in our study are in one or the other group, independent groups, one or the other. That's a between subject factor. A repeated factor is something that is changing, or we have different levels within the same person. So if we did a pre-test and a post-test on every person, then pre versus post time, that's repeated doing the test is repeated within the same subject. So in this second half of the semester, first we're going to do independent groups of ANOVA, one-way and then two-way, and then we're going to do repeated measures ANOVA, where we have repeating on people, and then we're going to put them together, and we call that a mixed design ANOVA, where we have independent groups and repeated measures, where you might have treatment and control, that's within subject, and repeated measures pre-test, post-test, which is more realistic of what you might do. But we're going to break it down first independent groups, one-way and two-way, and then repeated measures before we put those two together. That's the last ANOVA chapter. Okay. Side note here. We're doing groups here. We have more than two groups usually. The groups can be things that have no ordering, but sometimes our groups do have order. What if we were looking at first graders, second graders, third graders? Not only are those separate groups, but there is an ordering to the groups. We have first grade, and then second grade, and then third grade. What if we had grades 1 through 5? First, second, third, fourth, fifth. Anytime you have a very ordinal grouping variable, it's usually more powerful to do a regression instead of ANOVA, because ANOVA just treats them as different groups. It doesn't know or can't take into consideration the ordering of the groups. So if you have pre-test, post-test, that's only 2, but if you have pre-test, post-test, and a follow-up, ANOVA doesn't know the order that those came in. It is blind to order. So if you have ordering to your groups or your repeated measures, it's more powerful to use a regression approach than an ANOVA approach, which happens sometimes. Okay. Analysis of variance. The standard abbreviation ANOVA, ANOVA, is not a predefined term as far as APA is considering. So if you're writing this up in APA format for a journal article, your thesis, your dissertation, the first time you have to say analysis of variance and then in parentheses ANOVA before you can use the ANOVA abbreviation. Now on the homework you can use the ANOVA abbreviation, but just know that for writing articles and APA specified stuff, you've got to say the full analysis of variance the first time. I think that it should be accepted, but it's not. So we can use these for experimental, observational, or quasi-experimental. There are lots of other names for these. The simplest ANOVA. So the simplest ANOVA we're starting with is often called a one-way ANOVA. It can be called a single factor, a univariate ANOVA, a simple ANOVA, independent groups ANOVA, or between subjects ANOVA. All of those mean exactly the same thing. And which lingo you use depends on who you're talking to. I use all of those terms interchangeably. Some people are like, what do you mean? And then I say another one, they're like, oh yeah, got that one. It's just we have one way of grouping our subjects by one variable. And we're going to look at overall, this is the important word here, is omnibus test. It just says, are any of the groups different from any of the others in terms of their average? We're comparing the averages, we're comparing the means, and it's just overall. So if I have 10 group ANOVA, I'm just asking, is any one of those 10 groups different from any one of the others? It doesn't tell you which group is different, it just tells you at least one group is different. So for an ANOVA, we have one outcome variable we're comparing the average to. It has to be continuous or highly interval ratio and normally distributed. So that's an assumption for ANOVA, which is quite limiting, actually. This is another reason why ANOVA doesn't often fit, because your outcome, your thing you're comparing, has to be normally distributed within each group. And a lot of social science things are not normally distributed. And then we have one grouping variable that can have anywhere from usually 3 or more groups. If you have 10 groups, that gets really, really hard. Okay, so we're going to use this letter K. Whenever you see K, K means the number of groups. So if I have hemisphere stroke, right hemisphere stroke, and healthy controls, K is 3. And most of our examples will have K equal 3. Some will have K equal 4 or 5. Okay, there's this applet I wanted to show you. I use it every year. I love it. And the link has moved, and I cannot figure out where they put it. I cannot find a link to it. It's my favorite because it does ANOVA without numbers. But there's a recording of it on YouTube. Let's see. See, and even here, they have a link here. Oh, this is a slightly different one, I think. Yeah, this is a slightly different one. Okay. All right, so here is, what's K in this example? 4. These are like box plots. So we got 4 groups here. What are the group averages in this case? 0. What's the grand average? Grand average is the average of everything altogether. Yeah. Here we go. So here I can change the means. Oh. Now what do you think? What are the group averages? 5, 0, 0, 0. What happened to the grand average? It's not 0, it's a little bit up. Yeah. So there is, what would you say? Is one of those groups different? Yes. At least one group is different. Yep. Okay, what happens if I do this? I kept the averages all the same place. What did I do? I changed the spread, the standard deviation. Are any of those groups different? How confident are you that that first group's different?
Not really.
Why?
Because it's the low end of the range. It's within the
There's some overlap there, right? The average is still at 5 instead of 0. The averages of this group is 5 higher than all of those averages. But is 5 big? Not anymore. The difference in the averages is still 5. But 5, you can't just say how different are the averages. You have to also look at what's the amount of spread inside the groups. And that's what the F test, the ANOVA test, is trying to look at. Now let me bring those back down to what they were before. Okay. We'll come back to that in a minute. Okay, where's our PowerPoint? Okay. So let's look at it. This is a toy example. I think this might even be the one that's in the book. So we're going to do A, B, and C, 3 groups. We want to do a study to know if noise inhibits learning. Anyone listen to music when you study? Yep. What kind of music?
Does not have any words.
No words. No words?
I listen to music with words.
Music with words.
Depends on what I'm doing, though.
Depends on what you're studying. Okay. Well, here's a study. This is a fake study, by the way, but we'll pretend like it's real. We have 15 people. So we divided the 15 people into 3 groups. So each sample size is 5. And the first 5 people, group A, we put them in a room with no noise. The middle group of 5, we put them in with classical music, moderate noise, no words. The last group of 5, we put them in a rock music, extremely loud, banging room. And then we ask all these people to memorize a list of 15 nonsense words while they're in these rooms. And at the end, we ask them to tell us how many words, tell us the words back. And we count how many words they were able to memorize in the 1 minute. What do you think? Second group? Here's the data. In the quiet room, they remembered 8, 10, 9, 10, and 9. In the middle group, they remembered 7, 8, 5, 8, and 5. And in the loud, heavy rock, they remembered 4, 8, 7, 5, and 7. Eyeball test. What do you think? Does music make a difference? Yeah? Yeah. How so?
looks like Group A with the no noise,
Group A has higher numbers.
but
Maybe. How big are our samples? Really small. 5, 5, 5. That's not too great, right? Is there some spread even within group A? Is there any overlap between the words remembered in group A and B? There is some 8 is in both. There's 8 in both groups. There's 8 in all 3 groups. So we want to know, is there any statistically significant evidence that any of these groups are different? And if we find out there is, we want to know which one is different. Okay. Now, in a real study, we would probably have more than 5 per group, but I wanted this to be a small size so that we could work the numbers by hand. In real life, are you going to work these numbers by hand? Heck no. That's why we're using R. That's the whole point of learning R. Okay, so these are the steps for any hypothesis test. Always, this is a scientific method. You develop some hypothesis and state it in terms of a null and alternative. You go get some data and calculate your test statistic. Now, in the past, we've done Z, we've done T, and now we are finally going to learn F. And chi-squared is going to be the last week of this class. And then we're going to set our alpha level, which is usually 0.05. That's real boring. Decide if we want 1 or 2 tests, usually 2. We get our data, calculate rejection region, our test statistic, and see, what's our decision? Yes or no, we have evidence for our hypothesis. Same steps. Okay, so when we do an ANOVA, we now don't just have 2 groups that we're saying are equal. Now we have lots of groups. We'll have K groups, and for each group we'll have a mean, and for each group we'll have a standard deviation. So we use mu and sigma to represent the means and standard deviations of the whole populations. But what we really get are X bars and S's, means and standard deviations of our samples. So it's important in this blue box how we write our hypotheses. Our null hypothesis is that all the populations have the exact same average. So if our K is 3 groups, we'd have mu1 equals mu2 equals mu3, and that would be it. But you keep going however many groups you have. The null hypothesis is that all of the groups are equal. The alternative is not that. It's that at least one group is not the same as the others. You guys remember? You guys are probably too young. Sesame Street, and they'd put up the 4 pictures. One of these things is not like the other. One of these things just isn't the same. This is not how we write the null hypothesis. The null hypothesis is not that they are all different. It's that at least one of the groups has a different average. So in our music and noise and memorizing, our null hypothesis would be that the average words memorized with no music is the same as the average words memorized with moderate music is equal to also the average if you have extreme. All 3 of those are average. How would you write the alternative? At least one of the noise conditions results in a different average number of words memorized, not the null hypothesis. It's a little harder to write. I mean, this is short to write, but you can't write it as tidily as this, because it could be that none is different than moderate, or it could be that moderate is different than extreme, or maybe all 3 are different. The alternative hypothesis is any of those scenarios. Okay, so here's our data up in the corner. To be able to do this in R, you have to have this in that stacked long format. So each person gets a line. So how many people did we have in this data set? 15. So we need them stacked 15. Then this middle column has how many words they memorized, and then this third one is the group that they're in, A, B, C. This is how I've entered it. Now the columns could be in any order, but we need to have each person have their own line. So you could group by group. That's a really boring variable name. And we can ask for the furniture table 1 on outcome. So here we go. What are the averages? 9.1, 6.6, 6.2. Ooh, what do you think now? Is there a difference with music? Which group is different? A and B and C? They look similar. Now that's in terms of the averages. What else do we have for each group? An average and standard deviation. So there's group A, group B, group C. Okay, that's just showing animation. Okay. And here's a box plots comparing them. See, these box plots are very overlapping. Even though these overlap, it's to a lot lesser degree. Okay. Now, the languaging, your independent variable predictor, that's the grouping variable. If we're doing a table 1, we group by that grouping variable. And then our dependent variable, or outcome, that's what we're comparing the average of. That's what we would want to put in our table 1, or our y-axis. Okay. So, stats. When we do our stats, whether it's a t-test or an ANOVA or an r-squared, whatever we're doing it, we're always making a fraction, a ratio. And on top, we put all the stuff we can explain with our variables. And on the bottom, we put stuff we cannot explain with our random variable. A lot of times that's how we do it. How much can we explain? Remember when we did r-squared, we did the proportion of variance explained? A lot of times we do the same thing. That's what an F-test is looking at. An F-test, an F-score, an F-statistic, is a ratio or a fraction. It's what part of the variance in the outcome, the thing we're measuring, what part of the variance is explained by the groups, the difference between the groups, compared to what part of the variance, or what part is due to random error that we can't explain. Is everyone in group A the same? Is everyone in group B the same as everyone else in group B? Just knowing what group someone's in doesn't tell you everything. There's still other factors out there. So some of the score, some part of the score is explained by the grouping, and some part is explained by everything else. The wind, what side of the bed they woke up on, how old they are, did they have long toenails that hurt their shoes, everything else that might be different on a different day or with a different group of people. So what part of the variance is due to the difference between the groups versus within the groups, or random variation? F statistics are always built that way. So the numerator, or the top, is what is different between the groups. And the bottom is just random error, sampling error. This is why we get 2 degrees of freedom. The top is how many groups we have, -1. The bottom is sample size minus number of groups. We'll see that in a second. Okay. So the type of questions we can ask. We're asking, do the group means significantly different? Do the groups have different averages? Or are the averages just a little bit different, about what we would expect, because not everyone's the same? When we had that picture up there with those box plots, when they all had small spreads, and the average difference by 5, it was easy to say the groups were different. But when there was a lot of spread within the group, they overlapped a lot. So it was harder to make that distinction. So we're looking at the spread between the group averages compared to the spread within a group. Okay, there's a lot of words on this slide. Way too many words. Okay, your book had all these equations. Did you love that? How many equations were in this chapter? A lot. Here's the good news. You don't have to use hardly any of them. They took a long time to show you that if you started with the T formula, remember our good old T formula, and you did some algebra stuff, you can rewrite it, and when you get all done, you end up with this. Did you remember seeing this in your chapter? Yeah. An F value is essentially T squared. F is T squared. If you have 2 groups exactly, and you do the ANOVA, your F will be exactly the T of a t-test squared. Always. Guaranteed. It's a connection. So here's Mr. Ronald A. Fisher, agronomist. He did a lot of agricultural science. That's why he came up with ANOVA, because it works really well with the F distribution. We're going to skip a lot of this. This is what the picture of the F distribution looks like. Does that look like our bell curve, our normal curve? Not exactly. This is if our degrees of freedom are 1, 1. Does that look like a normal curve? No. Here's with degrees of freedom 3 and 10. Does that look like a normal curve? Well, coming. What if we get all the way down to 10 and 100 degrees of freedom? See, we have almost a normal curve here, but then we have this long tail. Now, this time we have 2 degrees of freedom with the numerator and degrees of freedom with the denominator, and both of them can be bigger or smaller. The denominator is always going to be a bigger number, usually. Okay, so that slide's just showing the same thing. Okay. In red, this is important. We want to know whether the variation among the group means exceeds the variation within groups. Is the next one going back? Here I do the calculations. I did an example showing you, here's our drug and placebo group we were playing with before. I can plug in their numbers, and I can find their t-squared, and it is exactly the F value. Yay. If you didn't believe the book, there's an example. Okay, assumptions. How important are assumptions? Really important. They're very, very important. Because if you violate the assumptions, your p-value is garbage. And you only know it's garbage if you bothered to look at the assumptions beforehand. And there are no stat police that are going to jump down from the air and say, hold it, you didn't check your assumptions. So you need to check them yourself. So these might look familiar. Do these look familiar? What's number 1? Independent, random samples, or at least representative. We cannot test that. We just must plan ahead. We're just going to have more than 2, probably now. Normal distribution of our outcome variable. Does that sound familiar? We don't have to use multivariate normal because we only have one variable. And the last one, homogeny of variance. Have we heard homogeny of variance before? Yeah. Before we used it, what do we use to test it? Levine's test. We still use Levine's test. We still use Levine's test to check for homogeny of variance. So ANOVA only works well, only tells us reliable results if all the groups have the same variance. Now, does it have to be an identical number? No. Kind of a rule of thumb to eyeball it. If any of the variances, not the standard deviation, the variances are more than double another one, then you usually have problems. You can do Levine's test to actually get the p-value, but that's kind of an eyeball test. Because the ANOVA uses, basically, it pools all your variances. Remember when we did the t-test on the test? You did Levine's test to decide, do we do a pooled variance, the regular t-test, or do we have to do the separate variance, Welch's test? Levine's test helps us know if we can do the ANOVA, which pools not just 2, but all of the group's variances. If we fail Levine's test, we should not use ANOVA. There is no separate variances ANOVA. There are other methods that are non-parametric you can use, but we're not going to learn them in this class. Okay. Yeah, there is a Welch's kind of adjustment, but it's not great. Okay, so the F statistic. The F statistic has a numerator and a denominator. The numerator is the mean squared between. Now, there are tons of formulas in your book. That's why I made the formula sheet, because it was trying its hardest, the authors, to put as little formulas in there, but it gets a little crowded. Okay, so this is the formula for the mean squared between. It's nice because if you have equal sample sizes, the formula simplifies. So if you have same size groups, which is the most powerful, which you want to plan for, then this is the nice formula you can use. If your groups are different sizes, you have to use the more complicated formula. The good news is in real life, do you have to do this by hand? No, you're just going to let R do it for you. You have to do 1 or 2 on the homework so that you can prove that you can use this stuff. Yeah. Okay. Okay, so this is the numerator, how different the group averages are. How different are the group averages? Then the denominator, oh, here we're going to do it. Here's our example. Now, our example, our groups were all size 5. That's nice. Then we can use the simple formula, right? Okay, so to find the top number for the F statistic, we do n. What in the world is n? Is it 15, 5, 10, or something else? 5. It's the common group size. 5 times, still it's the standard deviation of the x bars. Oh. How do we find the standard deviation? How many x bars are there? There's 3 x bars. If I have 3 numbers, how do I find the standard deviation between 3 numbers? Find the average. Subtract the average from each number. Square them. Then you add them up and divide. Now, when you add them up, do you divide by 3 or divide by 2? You do n minus 1 if you're doing the unbiased standard deviation. We learned all this jazz when? Way back in chapter 2, maybe? Yeah, a long time ago. And then you times it by n. Okay. So in this case, what's the top number of our F statistic going to be? $13.3. Okay. I chose this example because it's small. Okay, to find the bottom number for the denominator for the F statistic, again, we have 2 different formulas. We have the more complicated one if we have unequal group sizes, and then we have this one with equal group sizes. The homework tends to be more of these, I think. I think there might be one of those. Yeah. Yeah. Okay. So this is looking at the pooled variance. You can think of that bottom number as the pooled variance. Okay. Okay, so here's our data again. We got equal sample sizes. So let's see, what does the formula do? What does this formula tell us to do? Sigma means add up the variances and divide by number of groups, which is 3. So we add up. Now, are these variances 0.8? What do we need to do to make this a variance? Square it. So you take your 3 standard deviations, square them so they're variances, add them up, and divide by 3. 1.9. That is the bottom number of the F statistic. I only have you do a few on the homework and show you this so you know that this is not just like smoke and mirrors, that these numbers are really coming from someplace. So what is the bottom number of the F statistic? It is the pooled variance. Mean squared within is this grand pooled variance. And if we have equal sized groups, you just average the variances. If you have unequal sized group, you have to do a weighted average, and that's why that formula is a little bit more complicated. Okay, so our ANOVA. On the top number, it's the variance, how different the group averages vary from each other. The bottom number is how much what's that pooled variation on the bottom. So it's the effect of the independent variable over the random variation. There are too many words on these slides. Okay, let's go back to our little applet. The one that we found is a little different than that other one, but it works. Okay. So let's move this down. Oh, let me put this here. Okay. Okay, right now, how different are the group averages? Oh, it's not showing it there. You don't see it. That's not good. It's because it's extending, or it's, yeah, duplicate. Okay. There we go. Now you can see it. What are the group averages? Zeros. So what's the top number of the F statistic? What does the top number of the F statistics say? It says, how different are the group averages? 0. And then the bottom number of the F statistic is the pooled spread. How much spread is in each one of these groups? The numbers are here, so there's zeros and ones. So the pooled variation is 1, because each of the this group has a spread of 1, this group has a spread of 1, this group has a spread of 1. They all have spread of 1, so the pooled spread is 1. So down here, our F ratio. We have 0 difference between the groups, and 1 is the spread inside of a group, so our F statistic is also 1. There's our F ratio. What would happen if I made, let's make this group, let's put it all the way up to 5. There we go. What increased? Mean squared between. Now there is a bigger difference between these red lines. Those red lines are the group averages. What happened to the group averages? The group averages, instead of being all the same, we now have variation in the group averages. One group is high, and this other group is, well, all three of the other ones, I've kept it simple, are low. There is now variation in the group averages. How much variation? Well, this is the number, whatever it is on this number line. It's like, whatever that is. What's the denominator? The bottom number of the F statistic? It's the pooled the pooled variance. The pooled variance is also going to be, is still 1. So when we make the F statistic, it's this number divided by 1. So the blue is the top number of the F statistic. This is orange is the bottom number, which right now it's 1. And the purple number is our F statistic, or F ratio, or a fraction when we divide. So blue number divided by 1 gives us the purple number, okay? Let me see. Oh, I have to change it here. The other one I could drag and drop. Okay. What about now? What happened to our S statistic? Did the bottom number change? No, but the top number increased. What's going to happen if I move this third group up? Go back down? Because we have 3 that are the same and 1 that's different by 5. What would happen if I did? Is at least one group different? Yes. How big is our F statistic? Huge. Huge. It's like getting closer to 200. Now, we don't have exact numbers, but yeah. Okay. Let's see. Let's do like this. Okay. Is there evidence that at least one group is different? Probably. Why do you say probably?
Because the W and the Z are so far apart.
What about if you just look at W and Z? Is there any overlap? No. And look, what number is our F ratio? It's almost, 25, 30. It's pretty big. What is a statistically significant F value depends on your degrees of freedom, which depend on your sample size. But generally, even for small sample sizes, degrees of freedom, an F bigger than 10 is probably going to be significant. So that it's 20 or 30 is pretty significant. What's going to happen if I make the spreads bigger?
F ratio over down.
Is it going to change the top number?
No.
Didn't change the top number. What have I now changed? The denominator, the bottom number. This pooled standard deviation, instead of being 1, it's now going to be 5, 10, 2.5. Are these? Oh, these are standard deviations. So if the standard deviation is 2.5, the variance is 2.5 squared which is going to be between 4 and 9. 6? Does that look about 6? Yeah, the orange, the yellowish orange is 6. So now what's our F ratio? Blue divided by yellowish, purple. Probably not significant. What's going to happen if I make the spreads even bigger? Let me make the spreads as big as they can go. The centers, the group averages have stayed the same. So this variance, the spread between the group averages has stayed the same. But what have I increased? The spread within each group, the pooled standard deviation. So now what's our F ratio? Really small. And if we look at the groups, they overlap a ton. Does that picture help? I like the picture. I'm a picture person. Okay. Okay. So here's a picture. If all 3 of the groups have about the same center, our F statistic, our F ratio will be 1. If our groups are identical, the F ratio is 1. If our groups are different, our F ratio is bigger than 1. The further apart the groups are, and here they're shown with bell curves instead of those side-by-side box plots, but the more the groups are separated, the bigger the F ratio is. It gets bigger than 1, up to 20, 30, 100, 300, if they're really, really different. Okay, so the book goes through different ways to calculate these. There are 2 ways that you can do these by hand, if you're interested. And I think the homework has you do at least one of each. You can calculate the F ratio with summary statistics. So that's what we just did on the last slides. We had that table 1, so where we had the 3 groups averages and the 3 group standard deviations. You can do that. And usually in intro to stats classes, they teach you the formulas using the summary statistics. But that's not the way the computer is doing it. The computer does it in another method or approach called the sum of squared approach. And this is where we get our ANOVA table that has the sum of squared column and the mean sum of squared columns, because this is how the computer calculates it. So it actually calculates what are called sum of squared. This is sum of squared residuals. There's similar idea to regression residual. So if we take each value and subtract its average, that's the residual. And what do we do to the residuals? We square them and sum them. So that's where SS comes from, squaring and summing the residuals of our values. So the sum of squared total is how much variation there is in all of our data just lumped together. And we're going to partition or divide that variation out to the part of the variation or sum of squared that is explained and the part that's unexplained, or the part that's between the groups versus within the groups. So this formula, sum of squared total, is equal to the sum of squared between the group averages plus the sum of squared within each group. This formula, adding these 2 pieces up to the whole, that formula holds just for sum of squared. You cannot add up mean sum of squared, just sum of squareds. So the total sum of squared, that's the formula the book tells you. These are the degrees of freedom that go with the total. Degrees of freedom total are the total sample size minus 1. So on our toy example up here with the music and the memorizing words, what's n little t? What number? 15. So degrees of freedom t is 14. So NT is the total sample size, that's 15. So degrees of freedom total would be 14. Sum of squared between, there's that formula. Here are the degrees of freedom. Now this is the numerator. The top of the F statistic is the MS, mean sum of squared between. MS between is SS between divided by degrees of freedom between. Degrees of freedom between. It's between the groups. How many groups do we have? 3. We use the letter K in general. So in our example, what's the degrees of freedom between? 2 is number of groups minus 1. So the numerator degrees of freedom is number of groups minus 1. So that leaves us the denominator, the within. Sum is squared within. There's its formula. Isn't that beautiful? And here's degrees of freedom within. Now, sum of squareds add up. Degrees of freedom also add up. And that's how we come up with this. So it's total sample size minus K. Now, in our toy example, what was the total sample size? 15. What's K? 3. So the denominator degrees of freedom is 12. So for our toy example that we're doing up there, our F statistic, after an F, we have to put parentheses with 2 degrees of freedom. The first number is the degrees of freedom for the numerator, which is K minus 1. And the second one is degrees of freedom for the denominator. That's total sample size minus K. Okay, so we have a table for F. Yay! And it's set up different than Z and T, and this is the last thing we'll do. Okay? And then Wednesday, what are we going to do when we come back? R and homework questions. So bring your homework, because the homework has you do some by hand. So you should try the ones by hand before you come back on Wednesday, and we can go over and work together the hand worked calculations that you have problems on, because I'm guessing you're going to get stumped by at least one, because there's a really hard one in there. And then we'll go over how to do it in R. Because I want you to do it by hand, just so you believe the numbers the computer throws at you, that it's not just smoke and mirrors. Okay, you have to be careful with the F tables. Remember the Z table, there's only one Z table, but the T table, there would be lots of them, so you had to look at the top for the, you had to go degrees of freedom on the side and then the alpha across the top. Well, F tables, since we have 2 degrees of freedom, there's a different table for every alpha. So this table that we're going to use is for the alpha 0.05. But there's another almost exact table, but it says alpha equals 0.01. So when you use the F table in your book, make sure you're on the right page, because they're almost identical. You really have to look for what the alpha is. Okay? Now, you've got 2 degrees of freedom. The numerator, or top degree of freedom, the first one we list, is going across the top. The denominator, or second degree of freedom, is going down the side. And where they come together is your critical value. So it's another different table. So here's the example we're doing on the board. So that yellow is really light. So we just said our degrees of freedom are 2 and 12, since we have 3 groups and 15 subjects. Here's our calculations we did. Our mean squared between is 13.3. Our mean squared within. How are we going to calculate our F statistic? What number goes on top? The 13 point whatever. What number goes on the bottom? The 1.9. So I calculate that, and I get a number that's almost 7. Okay? So I would go to my table. 3 groups means we go numerator degrees of freedom 2. 15 minus 3 degrees of freedom 12. There's my critical value. The critical value is 3.86. So if the critical value is 3.86, but my calculated observed F statistic is almost 7, what can we say? We reject the null hypothesis that the groups are all equal, and we say there is evidence that at least one of those groups has a different average. At least one of those noise conditions. Now, we can't yet say which one's different, or if all of them are different, we have to do post hoc tests. And that's the next chapter. We won't worry about that till next week. This chapter, we're just doing the F test. Our conclusion will just be there's no evidence that any of them are different, or there is evidence that at least one is different. It won't be till next week that we figure out how to do which one of the groups is different, or are they all different? That's the post hoc test. Okay? So hand calculations on your own, give it a go. It might be really helpful this time to print out the worksheets for those hand calculating ones, if you want. On the worksheet, see, I have the formulas all ready for you to go there. Use these formulas. Here's a place to do your work.
So, is the summer class to this extent, is that happening?
We don't know. Do you know of someone who wants to take it?